Welcome, students, to Part 2 of our Chapter 16 Organic Chemistry lecture. I'll now introduce you to a few reduction reactions featured in Section 16.1. Before beginning, I should remind you that one way to quickly spot a reduction reaction in organic chemistry is to see if a molecule has gained bonds to hydrogen. If it has, then we can usually say that the molecule has been reduced. Hence, if a particular reaction hydrogenates a molecule, that is, if it places hydrogen atoms on a molecule, you will often hear me say that the molecule has been reduced. In our first reaction, you'll see that we can treat a nitrile, such as benzonitrile, shown here, with hydrogen gas and a special catalyst called Raney nickel. This completely hydrogenates or reduces the triple bond to give us benzylamine. By comparison, we can also reduce the nitro group in Nitro Benzene to an NH2 using hydrogen gas and palladium. This compound, you might remember from Chapter 15, is called aniline. A very important use for aniline is to treat it with sodium nitrite, NaNO2, and HCl. This converts it to benzene diazonium chloride, shown here. The mechanism of this reaction, which I won't cover here, is addressed in your text. More importantly, you should be asking, Mike, why would I ever want to make benzene diazonium chloride? The reason is because you can convert it into a lot of different substituted benzenes shown here. For example, if I take benzene diazonium chloride, shown here, and treat it with copper bromide, I can convert it into bromobenzene. In contrast, I can treat benzene diazonium chloride with copper chloride and convert it into chlorobenzene, shown here. I can also take benzene diazonium chloride and treat it with copper cyanide, shown here, and get phenylacetonitrile. This compound, phenylacetonitrile, is not accessible directly in one step from benzene itself. In other words, you can't directly take benzene and do a substitution reaction to put a C-triple-N onto it. So how in the world do you get a C-triple-N on benzene? You have to go through this sequence. That is, you have to take benzene, put an NO2 on it, then take that product, nitrobenzene, and convert it to aniline, shown here. Then take aniline, treat it with sodium nitrite and HCl to convert it to benzene diazonium chloride, and then treat that with copper cyanide. The cyanide then replaces the diazonium group to give you phenylacetonitrile, shown here. There are other products that you can make from benzene diazonium chloride that you cannot make directly from benzene. Here is an example. If we treat benzene diazonium chloride with potassium iodide, we can make iodobenzene, shown here. Separately, we can treat benzene diazonium chloride with acid to access phenol, shown here. Now you show me a way of directly accessing phenol from benzene. Can you? No, you can't. That's the reason why we have to use this diazonium salt as an intermediate. We can also form fluorobenzene from diazonium chloride, but we have to first of all replace the chloride with an alternate counter ion. So we react benzene diazonium chloride with HBF4, and we can replace the chloride counter ion with BF4-. If we then take this intermediate and treat it with HCl, it will replace the diazonium moiety with a fluorine. That is the way that we access fluorobenzene. These reactions with copper salts, by the way, are called Sandmeyer reactions. I really don't care if you remember that name, but for some reason when I think about it, it reminds me of Andy Samberg from Saturday Night Live, whom I think is very funny. I now want you to pause for a moment and write down and consider these reactions before we go on to the next topic. I now wish to remind you of the 5 aromatic substitution reactions I taught you in Chapter 15. These are collectively known as electrophilic aromatic substitution reactions. The first, halogenation, occurs when we treat benzene with chlorine or bromine and a complementary iron catalyst. The second and third, nitration and sulfonation, transpire as indicated here. The next reaction is the Friedel-Crafts alkylation reaction, where an alkyl group is placed on the benzene by reacting it with an alkyl chloride and aluminum trichloride catalyst. Friedel-Crafts acylation is similar, except that it places an acyl group on our benzene ring. For any of you who wish to review these reactions or their mechanisms, please consult our posted material for Chapter 15. I now have to teach you one more thing that might seem a little tangential. That is the definition of 3 words: ortho, meta, and para. You see, if you have 2 substituents on a benzene ring that are attached to carbons that are immediately adjacent to each other, as we see here, then we say that those substituents are ortho to each other. So in other words, I've got a substituent on carbon 1 and another substituent on carbon 2. These 2 substituents are in an ortho relationship to each other. In contrast, if you have 2 substituents that are in a 1-3 relationship, as shown here, then they are meta to each other. And lastly, if they are in a 1-4 relationship, then they are para to each other. Thus, we could call these compounds shown here ortho-dichlorobenzene, because the 2 chlorines are ortho to each other, meta-dimethylbenzene, because the 2 methyls are meta to each other, and para-chlorobenzaldehyde, because the 2 substituents are para to each other. This now provides the necessary background for us to begin addressing a very significant question. What if I do an electrophilic aromatic substitution reaction on a ring that already has a substituent on it? Let's say, for example, that I have a substituted benzene ring here, and I run a nitration reaction on it. Where does the NO2 end up? Does it end up ortho, meta, or para to the initial substituent? The answer to that question simply is, it depends on what the first substituent is. I'll now teach you how to categorize different substituents and use them to predict exactly where new ones will go. Generically speaking, substituents that donate electron density into the ring are Ortho-Para Directors. Substituents that suck electron density out of the ring are Meta-Directors. Here's a list of several Meta-Directors. You'll notice that they all have one thing in common. They suck. To be more specific, every one of these, except for Nr3+, has an atom, either a carbon, a nitrogen, or a sulfur, that's doubly or triply bonded to another atom that's more electronegative. I'll now say that again. Meta-directors, except for Nr3+, have an atom coming directly off of the benzene ring that's doubly or triply bonded to another atom that's more electronegative. Now let's look at each of these and make sure that what I just said isn't a lie. You'll see that here we have NO2. Now if I actually draw out NO2, it's got a nitrogen that's doubly bonded to one oxygen and singly bonded to another. So if an NO2 is coming off of a benzene ring, I have an atom that's doubly bonded to another atom that's more electronegative than itself. So that applies. Let's look at this SO3H. In this case, I've got a sulfur that's doubly bonded to one oxygen, doubly bonded to another oxygen, and singly bonded to an OH. So if I have an SO3H coming off of a benzene ring, I've got an atom that's doubly bonded to 2 other atoms that are more electronegative than itself. Let's look at this C-triple-N. If a C-triple-N is coming directly off of a benzene ring, I've got an atom, carbon, that's triply bonded to an atom, nitrogen, that's more electronegative than itself. In all of these examples, except for Nr3+, I've got a carbon atom that's doubly bonded to an oxygen atom, which is more electronegative than itself. So once again, this is what meta-directors look like. They are atoms immediately bonded to your benzene ring that are either doubly or triply bonded to other atoms that are more electronegative than themselves. The one exception is Nr3+, where R can be any alkyl groups or hydrogens. Let's now look at Ortho-Para Directors to compare. You'll see that they also have common characteristics with each other. Ortho-Para Directors, in fact, fall into one of two categories. Category 1 is alkyl groups. So if you have a benzene ring that has a boring carbon chain dangling off of it, which is considered an alkyl group, or a benzene ring, another benzene ring coming off of it, which is considered an aryl group. So these two groups that are carbons and hydrogens dangling off of it, those are Ortho-Para Directors of category 1. All of the other Ortho-Para Directors, including these halogens and all these oxygens and nitrogens, are in a different category. They all have atoms immediately stuck to a benzene ring that have at least one lone pair of electrons on them. So once again, I want to say that again. Ortho-Para Directors fall into one of two categories. Either they're alkyl or aryl substituents, or they're atoms stuck immediately to the benzene ring that have at least one lone pair on them. I want you to pause right now and think about these descriptions for a few minutes so that they can really sink in before we go on to the next slide. To recapitulate what I just taught, generically speaking, electron withdrawers, which are meta-directors, look like this. They are either an Nr3+, or they are atoms that are doubly or triply bonded to other atoms that are more electronegative than themselves. This is what electron withdrawers look like. They suck electron density out of a ring. So what's a good way of memorizing that withdrawers are also meta-directors? By remembering that W equals M. I realize this doesn't make any sense, but if you can remember that a W is really an upside-down M, then you can remember that withdrawers are meta-directors. Here, once again, is our list of examples of meta-directors. Now we'll return to our donors. Remember that generically speaking, donating groups, which are Ortho-Para Directors, look like this. They are either alkyl or aryl groups, or they're atoms immediately bonded to the benzene ring that have at least one lone pair of electrons on them. You can also have atoms that are immediately bonded to a benzene ring that are bonded to other atoms that aren't more electronegative than they. Is there a good way of memorizing that donors are also Ortho-Para Directors? Yes, there is. We have to remember that donors smoke dope. In other words, we can remember that donors are Ortho and Para Directors. DOP. I added the E because I thought it would be more easy to memorize dope instead of DOP. Here, once again, is our list of examples of donating substituents. You'll notice that once again, every single one of them has at least one lone pair of electrons on them, except for those that are alkyl or aryl substituents. Let's move on to some lecture problems. What are the products of the following reactions? Because I'm going to discuss the answers to these problems on the upcoming slides, this might be a good place for you to pause the video and attempt to do them first on your own. Here are the answers. First of all, in this problem I have Nitro Benzene, and I'm going to be treating it under these conditions, SO3 and H2SO4. H2SO4 and heat also will do the same exact thing. So where in the world, or what does this reaction do first of all? Well, we might remember from chapter 15 or from a few slides ago that what it does is it places an SO3H onto the ring. The question then arises, where does the SO3H go? Does it go ortho, meta, or para to this NO2? The answer has nothing to do with these reagents. All we do is look at the substituent that's already on the ring, and we ask ourselves, is this substituent an Ortho-Para director or is it a meta director? Now you'll remember that NO2 looks like a nitrogen that is doubly bonded to an oxygen on one side and singly bonded to an O- on the other. In other words, it's an atom that's doubly bonded to another atom that's more electronegative than it. Hence, it is a withdrawer. If we remember our little mnemonic device, we will remember that withdrawers are meta directors. Hence, the SO3H ends up being meta to the NO2. Let's go down to our second example. Here I have this starting material, toluene, and I treat it under the same conditions. I know that those conditions put an SO3H on the ring. But where does the SO3H end up? Does it end up ortho and para, or does it end up meta? Once again, the answer to that question depends completely on what this substituent is. Is it a withdrawer or is it a donor? You're right, you might remember that alkyl chains, including CH3s, are donors. We remember our mnemonic device DOPE. Donors make things go ortho and para. Hence we get a mixture of the SO3H being ortho to the methyl and the other product where the SO3H is para to the methyl group. Those are the products that we get in mixture. Now that might seem a little bit unfair for us to get a mixture of two products, and you might think that isn't very efficient. I would agree with you, but you should remember that when we synthesize these in real life, these two products are typically very easy to separate. So we can isolate exclusively the one that we desire. Let's look at our other examples. In this one, I've got this molecule, benzoic acid, being treated with nitric acid and catalytic sulfuric acid. What does this reaction do? Well, we remember from chapter 15 that it puts an NO2 on the ring. But where does that NO2 go? Does it go ortho and para to this substituent, or does it go meta to this substituent? Once again, the answer to that question has nothing to do with these reagents right here. It has everything to do with what this substituent is. So we look at this substituent and ask ourselves, is it a meta director or an ortho-para director? Well, this substituent has an atom that's doubly bonded to another atom more electronegative than itself. Hence, it is a withdrawer. We remember that W equals M, so it is going to put an NO2 meta to the initial substituent. Down here in this example, I'm doing a Friedel-Crafts alkylation. I'm going to be putting a CH2CH3 onto the ring. Where does it go? That depends completely upon the identity of this substituent. This substituent is a chlorine. What kind of substituent is that? Is it a donor or a withdrawer? Well, you'll remember that chlorine has lone pairs on it. You'll also remember from what I taught before that all of these atoms that have lone pairs on them, when they are bonded immediately to the benzene ring, are donors. We remember that donors make things go ortho and para. We use the mnemonic device DOPE. Hence, we will get a mixture of the ortho product and the para product. Now let's look at this slightly more complex example. Which benzene ring am I picking to put my substituent on? Well, it doesn't really matter because this molecule is completely symmetrical down the middle. So I am going to, just for the fun of it, arbitrarily pretend that this is the benzene ring we're going to put our acyl substituent on, using this Friedel-Crafts acylation reaction. I then look at the rest of this thing as being a substituent dangling off of this benzene ring. What kind of substituent is it? Well, as I have indicated here, it is a donor. Why? Because I've got an oxygen. An oxygen has at least one lone pair, actually two lone pairs, and it's bonded immediately to this benzene ring. Hence, the substituent that's placed on this ring, this acyl substituent, ends up going ortho and para in a mixture. Now we come to slide 25. This might seem like an odd reaction for me to throw in here because it actually comes from the first half of our Chapter 16 presentation. Nevertheless, I wanted to include it just to keep you guys on your toes. You'll remember that when we treat an alkylated benzene with KMNO4 water, MnO2, or sodium dichromate, it will convert any and all benzylic carbons to benzoic acid if those benzylic carbons are bonded to at least one hydrogen. So when we consider this reaction, we have to ask ourselves one question. Does this benzylic carbon have at least one hydrogen bonded to it? If the answer is yes, and it is, then it will get converted to benzoic acid. But wait, are there any other benzylic carbons here? Why, yes, there are. It's this one. So we have to ask ourselves this question. Does this benzylic carbon also have at least one hydrogen bonded to it? The answer is yes. Hence, when we run this reaction, KMNO4 water, what occurs is both of these benzylic carbons are converted to benzoic acid. The final product I end up getting is dibenzoic acid. Now that I've introduced you to the concept of Ortho-Para and meta-directors, I hope you're wondering, why are Ortho-Para directors Ortho-Para directors? To begin answering this question, we have to review or remember that all electrophilic aromatic substitution reactions follow this general mechanism. I begin with benzene, and electrons come out of benzene and grab some electrophilic group, making this intermediate. Then a base comes in, steals that hydrogen, and dumps the electrons in like a door closing on a hinge to regenerate aromaticity. Once again, I want you to look at this mechanism and remember that whenever we do an electrophilic aromatic substitution reaction, the E plus will end up being placed on the carbon atom in the ring that's the juiciest, that is, the one that has the most electron density, the most electron juicy position. Why? Because that's the position that has to reach out with its electrons and grab that E plus. This brings us now to our Ortho-Para directors. As we already discussed, most Ortho-Para directors have atoms bonded to the ring that possess at least one or more lone pair of electrons. To show you what this does, I've chosen this generic Ortho-Para director as an example. And I will prove to you that this oxygen right here pushes electron density into the ortho and para positions. How do I prove that? By drawing resonance structures. So here's what we do. If I have the lone pairs on this oxygen, one of the lone pairs thrust into the ring, and then push those pi electrons on to that ortho position, you'll see that this is a legitimate resonance structure. If I then have these electrons come down to form a double bond there and push these electrons onto that position, this is a second resonance structure. What can I do now? Well, I can take these, this negative charge, push it down there to form a double bond, and thrust these pi electrons onto that position, giving this resonance structure. If that negative charge is then thrust in, and those electrons back onto the oxygen, I go back to where I began. You'll notice then that in all of these different resonance structures, I've got a partial negative charge sitting on the ortho position, on the para position, and on the ortho position relative to this initial substituent. In other words, substituents that have at least one lone pair can donate that lone pair in and put partial negative charges on the ortho and para positions. Hence, these are the positions that have the most electron density. They are the most electron juicy. Hence, these are the positions that will do the attacking, or will attack an E+ during an electrophilic aromatic substitution reaction. I want to state that one more time. Because Ortho-Para Directors thrust lone pairs into the ring by resonance, if you draw all of the resonance structures, you will see negative charges being placed on the ortho and para positions relative to the initial substituent. Having this partial minus charge on the ortho and para positions juices those positions up, making them the most reactive and the ones that will reach out and grab an E+ during an electrophilic aromatic substitution reaction. That is why Ortho-Para Directors place substituents ortho and para to them. I'm going to recapitulate this again. Because Ortho-Para Directors place partial negative charges on the ortho and para positions to them through resonance, these positions are the juiciest. Hence, those are the positions that will place E+ on them during an electrophilic aromatic substitution. That is why an Ortho-Para Director gives a mixture of products ortho and para. Question you might ask is, Mike, do you want me to be able to explain why Ortho-Para Directors are Ortho-Para Directors on an exam? The answer is yes, and you had best be able to draw all of these resonance structures and use them in your explanation. Now I'll show you why meta-directors are meta-directors. Remember that meta-directors are withdrawers. That is, they suck electron density out of a ring. To show you this, I've chosen this generic meta-director as an example. And I will prove to you that it sucks electron density out of the ortho and para positions. How? By using resonance. So if I begin here with this material that has a withdrawing substituent on it, I can suck electrons into that oxygen and suck electrons out of the ring, giving me this resonance structure right here. If I then flip those electrons like a door on a hinge to close that positive charge, I end up with a positive charge at this position. If I then flip these pi electrons in to close that positive charge, I end up with another positive charge at this position. If I then push the electrons from my O- back down and push these electrons in to close that positive charge, I end up going back to where I started. So let's look at this for a moment. You will notice that this withdrawing substituent, by a resonance, ends up placing a positive charge on the ortho and para positions relative to it. Do you see that? Hence, it deactivates those positions and makes them the least juicy. In other words, a withdrawing substituent sucks electron density from the ortho positions and the para position. Hence, by default, the only position left with electron density to reach out and attack an electrophile with is the meta position. I'm going to say that one more time on this slide. Because withdrawers suck electron density from the ortho and para positions by resonance, the only position left with enough electron density to attack an E+ is the meta position. That is why withdrawing substituents are meta-directors. You might ask me the question then, Mike, do you want me to be able to explain why a meta-director is a meta-director on an exam? The answer is yes, and you had best be able to draw all of these resonance structures to prove it. This, I think, is a great place for us to stop our second video from Chapter 16. Please take a break, a whiz, a dump, or whatever else you need to do to get recharged. Then return and watch the next and final video segment from Chapter 16.